Morning. This is B. Naresh, working as assistant professor in EC department. And today's topic is Halfwave Rectifier. So before going to this section, so what is actually rectifier? The rectifier is a circuit and it can be used to convert the AC voltage to the pulsating DC signal here. So if you want to process this conversion to convert the AC signal to the pulsating DC signal, you can use either one or more PN junction diodes. So by using these PN junction diodes, we are going to design a rectified circuit here. So in this process, if you are observing the AC signal, the AC signal contains like this. For every clock cycle, it reverses the direction. So some amount of the time period, it is represented as a positive direction. And after some t1 instant, again it reverses the direction. So that is the reason in an AC waveform, it regularly reverses the direction here. But coming to your DC, it allows only in one direction only, either the positive portion or your negative portion here. So here, so why we are going to process this? Why we are going to convert this AC signal to your DC signal? But actually, by using this rectifier, it converts only the AC signal to your pulsating DC signal. Why? Because of that, most of the electronic devices requires a DC signal. So hence, we are going to convert a analog means AC signal to your DC signal here. So coming to here, we have the different types of the rectifiers here. The first one is half-wave rectifier, and the second one is full-wave rectifier, and the third one is the bridge rectifier here. So in this today's session, we are going to discuss half-wave rectifier and the analysis of some parameters related to the half-wave rectifier here. And coming to this half-wave rectifier, and we know that the rectifier is used to convert a AC signal to the pulsating DC signal here. But based on this representation of half-wave rectifier, it allows only either one portion, either the positive portion or negative portion. And another portion is blocked by your given PN junction diode. So based on the utilization of the diode in the circuit, this half-wave rectifier allows only one of the portion and alienated by another portion here. So that is the reason. So we are going to observe how this PN junction diode allows either one of the portion. Either it should be a positive peak portion or it should be a negative peak portion based on the utilization of the PN junction diode in a circuit here. So from that point, the half-wave rectifier, it contains only half of the input at the output side here. To process this case here, so it contains majorly three sections here. One is a diode is required, then a transformer, another one is a resistive load here. So these are the three important parameters. By using these three important parameters, we are going to design a half-wave rectifier circuit. So in this case, we are going to use only one PN junction, and that is nothing but a diode. And this transformer and another one is resistive load. By combining these three network components, then we are going to construct a half-wave rectifier. And coming to this half-wave rectifier, and we are having the three different sections here. One is the input side, we are having the AC source section. So here we are going to apply a 230 volts AC signal here, and generally, and we are having the frequency is 50 Hz frequency here. According to Indian standard, we are having the frequency is the 50 Hz here. And this 230 volts is why? Because of that, why we are using this transformer here. So here, the diode can be operated at certain minimum voltage here. So that is the reason. To withstand this diode, then we need to reduce this 230 volts to some voltage here. For this case, we are going to use the transformer section. By using this transformer section, we are reducing this 230 volts to some required AC voltage, and that AC voltage is passing through the secondary winding. So here this transformer contains two windings here, and this is primary winding here, and this winding here it is called as the secondary winding. Then by using the secondary winding, we are going to connect the PN junction, and this is the PN junction, and it is represented as the diode D here. And here, this is the load resistance here. So this is represented as 0R. But internally, this diode is also offers a diode forward resistance as well as the diode reverse resistance here. But based on the biasing, and we know that the diode contains very small forward resistance and it offers a infinite reverse resistance. So here we are in the three majorly. So one is the transformer section, and by using this diode, we are rectifying. Means our main intention is to convert the your given analog AC signal to a pulsating DC output. But actually, what is the pulsating DC means? It's not exactly pure DC signal. It contains a DC signal along with the AC harmonics here, along with the AC signal here. So that type of the signal is called as the pulsating DC signal here. Then if you want to remove this completely ripples or AC component, then we go for another one is filters concept here. But here, by using this diode, we are processing the AC signal to the pulsating DC signal, and that process is called as a rectification process here. So that is the reason this section is represented as rectifying section. And then now we are going to observe the response of this rectification across the load here. So hence we are going to place a load resistance to this rectifying section. By using this load, we are going to observe the response of the rectifier. Then we need to observe how this halfway rectifier allows only the one portion, either the positive portion or the negative portion, based on the utilization of this diode. Based on the utilization of this diode in a circuit. So here I made this one. We can also remove this diode, but operation will be different. So that is the reason by using these three major sections, by using the transformer section, rectifying section contains only the diode here, but here it contains only one PN junction here. And the load section contains a load resistance RE. So by using this process, now this circuit it processes the AC signal to the pulsating DC signal. And why it is called as half-wave rectifier means it allows only the one of the portion. Either it allows the positive portion or negative portion of your given analog input signal or AC signal. We need to observe that one here. So from that response, we can say that the circuit is acts as a half-wave rectifier. So now we'll see the operation of half-wave rectifier here. So for this case, we are going to apply here. Let us, if you observe the circuit here, we are going to apply the 230 volts AC signal with a frequency of 50 Hz. So that is the reason. Let us consider this is your given input signal. The input signal contains two peaks. One is 0 to pi duration. This is a 0 to pi duration. And this 0 to pi duration, we are having the positive off cycle. And pi to 2 pi duration, we are having the negative off cycle. 0 to pi duration, positive off peak, and pi to 2 pi, the negative cycle. So hence, and the given signal contain some magnitude. The magnitude is represented as your Vm. Hence, from this a graphical representation, the input signal is represented as Vi or V is equal to, and it contains a magnitude, and this wave is represented as a sinusoidal nature here. And this pulse signal is linearly varies with respect to your time period. So hence, the given input signal is represented as V is equal to Vm sine omega t here. And the duration is, what is the duration of one given input signal? This is one clock cycle. And this is one clock cycle here. And the duration is 0 to 2 pi here. So that is the reason. The omega t duration is 0 to 2 pi here. So hence, in a mathematically, the signal is represented as Vm sine omega t. So here 0 to pi, the peak is represented as a positive magnitude, and pi to 2 pi duration, the peak is represented as a negative peak here. And now we need to observe. So we are going to apply this given input signal to a rectifying section. Then how it is allows some portion of the given input signal, and how it is attenuates the another portion of your given signal. So for this case, we are going to observe the two different cases here. The one case is when we are going to apply the positive, or when the signal is passing through this positive off cycle. And the second case, now we are going to observe when the signal is passing through this negative peaking. So that is the reason. Let us assume here, and this is your off-wave rectifier circuit. So here we are going to apply a V, and here we are representing that Vm sine omega t here. And we know that the duration is, what is the input here? V is equal to Vm sine omega t, and the duration is 0 to 2 pi. But in that 0 to 2 pi, the first case, I am going to assume only the positive peak. So here, this is a positive peak. Let us assume what happens when the input signal changes from the 0 to Vm and again Vm to 0, or this 0 to pi duration. So in the first case, we taken as this is the 0 to pi duration here. So before going to this, and first I'm going to recall this diode operation. And from the diode operation, the PN junction diode, or if you consider this PN junction diode, and this is the anode side, and this is the cathode side. If you made this is a forward bias, and under this condition, here the diode acts as a forward bias. Under the forward bias, we can represent it as your short circuit. So here I consider the ideal condition. The diode I am assumed as the ideal diode. So under the ideal diode characteristics, when we apply the forward bias to the PN junction diode, the diode acts as a forward bias. Under this forward bias mode, the diode is replaced with a short circuit. And similarly, if the diode is operated under the reverse bias, if suppose the anode is connected to negative pole of the battery and the cathode is connected to positive pole of the battery, then the diode is configured as reverse bias. Under this reverse bias, so what happens here, the diode acts as a reverse bias. Under this reverse bias, diode is replaced with the open circuit, means there is no flow of current across the given circuit. Now, based on these two observations from the diode characteristics, now I am going to apply these parameters to this diode condition C. At this point, here I am applying the positive peak duration. So what is the positive peak here? The duration is 0 to pi duration. during this 0 to pi duration. So what happens here means a positive pole is connected here and a negative pole is connected to this lower potential, means this is the ground potential. Hence, the positive potential is connected to anode. This is the anode of the diode, and a cathode of the diode is connected to a negative potential. So from this way, we can say that, so here the diode is acts as your forward bias here. So hence, so what happens here at this point, diode is acts as your forward bias. And from this analysis, what we assumed here, if the diode is enters into the forward bias, the diode is a replaced with your short circuit. Means this diode is a replaced with your short circuit. So what happens here? The current is flowing through this network here. So hence, during the positive portion of your given input signal, anode is made with a positive polarity and a cathode is made with a negative polarity. Then the diode is enters into the forward bias diode. Hence, here this diode is replaced with a short circuit. So hence, the current is flowing from. So how the current is flowing here? Now the current is flowing from a node to the towards the diode, towards the load resistance, then towards the B node here. So hence, and this is the current flow direction. The red color lines here I'm indicating as the current flowing direction during the positive portion. So why this current is flowing? Flowing from A node to the B node. Why? Because of the here the diode is represented as your short circuit. So why? Because of the diode is acts as your forward bias. So that is the reason. During the positive portion of a given input signal, based on this construction of this diode is acts as a forward bias. Hence, it is a replaced with a short circuit. That is the reason the current flowing through this network from the A node to the B node through the diode and your load resistance C. So similarly, now what happens here? So here, what is the output of so and at this point, and what is the response of the given input signal? Now here we are going to measure the response across this load resistance. Now the current is the maximum current is flowing through this load resistance as well as the diode. But when the diode is a forward bias and this diode is replaced with a short circuit, and hence internally it contains a diode forward resistance. And in this case, let us assume that the diode forward resistance is a very small compared with this low resistance. So here I am assuming this, the diode forward resistance is much less than of RL. What happens here means the maximum current flowing through this load resistance only. So hence, here the given input signal is linearly changes from 0 to Vm and Vm to 0 in the duration of 0 to pi. Hence, the output is also, so here this is R is a linear, so linearly here the current is also linearly, means the maximum current, whatever the current is generated with respect you are applied according to Ohm's law. So I is equal to your V by R. So means here R is made as a constant. So I is directly proportional to your V. So hence the same amount of conduction flows across this load resistance. That is the reason the response of Halfwave rectifier is represented as, means it allows this entire the positive portion. So hence the output is represented as this signal here during the positive portion of given input signal. Similarly, we'll see what happens if the negative peak is passing through this rectified circuit. Let us take, here I consider the negative peak, the same signal I consider V is equal to Vm sin omega t. And again, we are in the transformer section, and this is the rectification section, and the load resistance R here. So here we are going to consider the peak is a negative peak, means the duration is, what is the duration? Pi to your 2 pi duration. The duration is pi to 2 pi duration. During this negative peak duration, now we'll see what happens. Means, so here the negative polarity is connected with respect to your opposite. Means here the positive node is a connector. So for this point, so hence it is represented as the negative polarity, and here it is represented as a positive. So but coming to this diode, this is anode and this is the cathode, and the negative polarity is passing through the anode, and a cathode is connected to positive polarity. When we are passing this negative peak, the duration we are assuming here, a pi to 2 pi duration, the negative polarity is connected to anode of the PN junction diode, and positive polarity is connected to your cathode of the PN junction diode. Under this condition, now we know that, so let us say this is the PN junction, anode and a cathode. If anode is connected to negative polarity of the battery with respect to the cathode, and the positive polarity is connected, at this point the diode acts as your reverse bias. Under this condition, here the diode is replaced with the open circuit. So hence, during this negative peak cycle, the diode is replaced with the open circuit. Why? Because of that, here the diode acts as your reverse bias diode. So hence, if the diode is replaced with the open circuit, so means at this point here this is acts as a like. So means there is no current flowing through this network. So at this point, so it breaks the continuity in this circuit. That is the reason. There is no flow of the current from the A node to the B node through this load resistance. Hence, so here the maximum current flowing is through this resistance is 0 under this negative clock cycle or negative peak signal. So that is the reason. The output is represented as your 0. So hence, entire the peak duration, the output is represented as your 0. So based on this positive off cycle and negative off cycle, so here we observe the responses here. So what we observe here, in a positive peak duration, it allows the positive peak signal, but during the negative off cycle, it attenuates that given negative off cycle. So that is the reason. It allows only the one portion of your given input signal. Hence, it is called as, this process is called as your half-wave rectifier process here. So from that point, let us consider here the output waveform. Here I represented here. This is, let us say, the first one, the first graphical representation is the input signal. So this is your input signal, and here I consider the different clock cycles here. So one is, here I consider some 0 to 2 pi duration. So this is positive peak duration and this is negative peak. And we observe during the positive portion of the signal, what is output here? So at this point, diode is acts as a forward bias. Hence, the diode is replaced with a short circuit. That is the reason it allows the maximum current. The current is generated here. So hence, across the load resistance, we observe the same response here. Similarly, what happens in the pi to 2 pi or negative peak cycle? At this point, what happens here? Diode is acts as a reverse bias. Hence, so here it is acts as a reverse bias. Hence, diode is replaced with a open circuit. Hence, there is no flow of current. I is represented as your 0. So similarly, again when a positive peak is occurs, then it allows the positive portion. When a negative peak is passing through this network, then it attenuates this signal. So from this, the output signal, how to write this output voltage. So the output voltage is contains only one portion of your given input signal. Hence, the output voltage is represented as V is equal to Vm. And again, the magnitude is the same magnitude, linearly changed. So Vm, and it linearly changes with respect to your time period. Hence, it is represented as V is equal to, that V is nothing but your output voltage V naught. V naught is equal to Vm sine omega t. But we are in the two different output cases. 0 to pi duration only we are having the response, hence, and this Vm sine omega t is only the duration of 0 to pi duration. And V naught is a 0 and the duration is pi to 2 pi duration here. So this is the output voltage of your given half-wave rectifier response here. Now, before going to this, now what are the, based on this operation, what are the parameters we need to observe here? So these are some important parameters we need to analyze from the rectifier concept here. So first one is DC output current, second one is DC output voltage, third one is RMS current, fourth one is RMS voltage, ripple factor, efficiency, output frequency, and peak inverse voltage, peak factor, and form factor. So these are some parameters we need to observe from the rectifier analysis here. We'll see in detail one by one here. So before going this, again, first we need to calculate, if you want to determine the DC output current, first we need to observe how much current is flowing across the load resistance during the positive peak portion as well as during the negative peak portion. So for this case, so from this response, so according to Ohm's law, we made as a load resistance is a constant. If the load resistance is a constant, I is directly proportional to voltage. So means the output current is directly proportional to output voltage V naught. And we observe this output voltage. The V naught is represented as Vm sine omega t. The duration is 0 to pi duration. And V naught is a 0 and the duration of pi to 2 pi duration. Similarly, by using this response and according to Ohm's law, based on the load resistance the constant, here I drawn the response of the peak current, how much magnitude of current is flowing through the rectification circuit. So hence I represented this I here. So means I is directly proportional to V, output voltage. So what is this one? With the magnitude of Vm sine omega t. So hence here the current magnitude is represented as your Im. Hence I is represented as Im sine omega t. The duration is 0 to pi duration. And again during the negative off cycle, there is no current. Hence this pi to 2 pi duration, the current flowing across the half-wave rectifier circuit is 0. Hence, I is represented as 0 with the duration of pi to 2 pi duration. So, by using these two parameters, now we are going to analyze the parameters of half-wave rectifier. So, now first I am going to observe this parameter. This is average or DC output current. So how much DC current is flowing across the load resistance or the given half-wave rectifier circuit. For this case, it is defined as this average or DC current is defined as is the area of the one cycle of the given curve is divided by the base. Is defined as the area of the one cycle of the curve is divided by the base. So, and here graphically I am representing as two responses here. One is the input signal Another one is the output signal. From the analysis of your Halfwave rectifier, during the positive portion, it contains a output signal is represented as Vm sin omega t. During the negative portion, this output voltage is represented as 0. Now, how to calculate this area of a given signal? If you want to calculate the area of a given signal, we need to apply the integral function. Now, what is the base here? The base is total time period. The max for a given clock cycle, the total base is 0 to 2 pi, means the base is 2 pi. So, based on this definition, the DC current is represented as area, means area of one cycle. So, one cycle means, let us take 0 to t. This is 0 to t means one cycle. And this 0 to t is represented as 0 to 2 pi. And is divided with the base. Again, this is the base. And we need to take of your curve. What is the curve contains your current? We are going to identify the current here. Hence, the current is represented as I into d omega t. So, linearly changes with your omega t. So, by using this formula, based on the definition here, and from this graphical response, the base is represented as your 2 pi. So, hence, here I represented this one. In the place of base, I represented the 2 pi, and the duration is a one cycle. One cycle contains the intervals of 0 to 2 pi I into d omega t. Now, but during this cycle, when the two output currents 0 to pi, the output current is represented as Im sin omega t. But pi to 2 pi, the current is represented as 0. Hence, I am going to write in this way. So, hence, IDC is equal to, this is a common 1 by 2 pi. So, 0 to pi, the current is again I into d omega t. There are the two responses here. Why? Because of that. So, here, if you observe this response, there are the two responses. 0 to pi. So, here we are on the 0 to pi and again pi to 2 pi response. So, hence, here I represented the two cycles here, 0 to pi as well as your pi to 2 pi. But pi to 2 pi, the current is 0 here. So, that is the reason 0 into d omega t. Here I am going to substitute what is I here. So, hence, what is I? We observe this I is equal to Im sin omega t. So, hence, IDC is equal to 1 by 2 pi integral 0 to pi. I is replaced with, what is I value? Im sin omega t into d omega t. But during the interval of pi to 2 pi, there is no current, hence it is represented as your 0. Now you can apply the integral of this function. Here this magnitude is a constant, you can take the outside. So I take in this outside, IDC is equal to Im by 2 pi. The integral of sine is minus cos. Then apply the limits are 0 to pi. You can apply this limit. So, Im by 2 pi, this is minus of cos pi minus cos 0. So, if you apply the limits, so cos pi is a minus 1, again cos 0 is a 1. Then after simplification, we got this Im by 2 pi into 2. This 2 is a get cancelled. Then it is represented as Im by pi. So, means the average or a DC output current is represented as Im by pi. If you want to write in terms of voltage, how to write this in terms of voltage? According to Ohm's law, I is defined as it is a ratio of voltage to your current. So, hence, I am going to replace this one I in terms of voltage and resistance. So, hence, Vm by R. R means, so actually this is IDC is equal to, this is Im by pi. Im I am going to write in terms of Vm by pi into R, where R is nothing but a, from the circuit, where I am the two resistances here. One is, when the diode is a forward bias, it offers a diode forward resistance, as well as it contains a load resistance is RL. So that is the reason. The summation of the diode forward resistance and load resistance here. But If you made this one, if RF is much less than of RL, IDC is becomes VM by pi into RL. Okay. Then next one is a average or DC output voltage. So now the second parameter is we need to calculate the DC output voltage. It is represented as VDC here. So generally, in general, VDC is equal to the product of IDC and your RL in terms of DC current and your load resistance. Now we got this IDC value. What is IDC value? We observed here VM by IDC. Just now we observed this IDC is equal to VM by pi into RF plus RL. Then this IDC is replaced with this parameter. So here the IDC is equal to VM by pi into RF plus your RL. And product of the load resistance is a load resistance here. Further simplification, if I made this one condition, if RF is much less than RL, why I'm taking on this RF is much less than of RL, and based on the biasing characteristics of a PN junction diode, it offers a very small forward resistance here. That is the reason. Always the diode forward resistance is much less than of your the given load resistance. Under this condition, we are going to neglect this a diode forward resistance. Hence, it is represented as the VDC is equal to. So what happens here? So under this condition, so what happens here? If I am writing this, VDC is equal to VM by pi. If RF is neglected, this is RL into your RL. So here I am neglecting this RF under this condition. If RF is a much less than of RL, I am going to neglect this diode forward resistance. Means I am assumed as a 0. If RF is a 0, 0 plus RL it becomes RL. So this RL is a get cancelled. Then VDC value it gives that VM by pi. So this is the DC output voltage is VDC is equal to VM by pi. So similarly, we need to calculate a root main square current here, IRMS here. So the definition is the same. IRMS is equal to the square root of your IDC current. So hence 1 by 2 integral of 0 to 2 I square into d omega t. So we'll again apply the limits here 0 to 2 pi I square into d omega t. And we are on the two responses here 0 to pi we are on the current the Im sin omega t, and 0 this is pi to 2 pi and there is no current, that is represented as your 0. Just apply the integrals here. Then the integral of this sin square theta is 1 minus cos 2 omega t by 2. Then apply the limits. Then simplify this one. So after this simplification, then so what happens here? Just you can apply the integral here. Integral of 0 to pi into 1 minus cos 2 omega t into d omega t. Just apply the integral function. So the integral of constant is with respect to omega t is omega t. Integral of cos is sine by t. Theta means theta by 2 here. So here the 2 is here. Then apply the limits here 0 to pi. So this is for omega t, this is limits are 5 and 0. And similarly for the sine 2 omega t, you can apply the limits. In the place of omega t, you can substitute the limits pi, sine 2 pi and sine 0 pi 2. So here this what happens here 5 minus 0 means pi. So sine n phi is a 0 and sine 0 is also 0 here. So hence, so sine, we know that sine n pi is 0. Sine 0 degrees is also your 0 here. 0 minus 0, 0. 0 by something is a 0. And here this is pi minus 0 is a pi. Then after this, so the square root is a cancel. So what happens here? The square and cancel. The square root of 4 is nothing but a 2 here. So hence, the root mean square current is IRMS is Im by 2. So if you want to write in terms of voltage magnitude, so this is represented by Im is nothing but a V by R. So hence, Vm by R. R means the summation of diode forward resistance and your load resistance. Hence, this Im is represented as Vm by RF plus your RL. So here I'm going to substitute here. Then it goes this IRMS is equal to Vm by 2 times of Rm plus your RL. So this is root mean square current here. Similarly, if you want to calculate the RMS voltage, VRMS here, so simply the product of IRMS into RL. So just now we observe the IRMS here. IRMS is, what is IRF value? Vm by 2 times of RF plus RL into RL. Again, if you make this condition, if RF, further simplification, if RF is much less than of RL, then what happens here? This VRMS becomes Vm by 2 times of RF is neglected, 0 plus RL into your RL. Means this RL is a get cancelled. The VRMS becomes your Vm by 2. So this is your VRMS is equal to Vm by 2. Now this is the most important. So based on the definition of the ripple rectifier, the rectifier is a process of to convert the AC signal to the pulsating DC signal. So what is the pulsating DC signal? The pulsating DC signal contains a DC output DC voltage along with the AC components. Now we need to identify that how many ripples will be occurred in a rectified output here. That should be measured by using this factor. The factor is called as your ripple factor. So for this case, the ripple factor is defined as it is a ratio of RMS value of AC component to the DC component here. It is defined as RMS value of AC component to the DC component here. So based on this, it is represented as IRMS to the IDC. And from this way, we know that IRMS is represented as the square root of I square RMS minus I square dt. If you want to simplify this one, I taken this IDC is divided within these terms. Now I'm making like this. So IDC is divided with this term and this term. Then becomes IRMS by IDC whole square minus 1. Now you can substitute this IRMS value and IDC values. So we got this, just now we observed this IRMS values and your IDC values. Just you can substitute here. So from this case, IRMS is Im by 2. IDC value is Im by 5. Just substitute here, this one. Then this becomes your pi by 2 whole square minus 1. Just substitute the pi value. Then simplify this one. The ripple factor, it gives that 1.21 here. So means that this amount of ripples will be occurred in a rectified output by using this half-wave rectifier analysis. So up to this point, today we'll discuss what is the rectifier and what is the analysis of half-wave rectifier. Then we also observe some of the important parameters in a half-wave rectifier. So thank you.
Like, share and subscribe. Hit the bell icon for more updates.